Assalamu alaikum, everybody. Welcome to this second lecture. In this session, I'll be talking about the measures of variability. I hope you remember that we have covered the measures of location in the first lecture. So let us just go there. But before I start this section, um, let me tell you that I've solved a few problems from the exercises of the previous section, that was the measures of location. So let me just show them to you. The problems that I've solved for you, you can just take a look at them. I hope I have them here. So yes, these were the exercises. So the section that is covering the locational measures, there are three problems that I've solved for you. So question number 9, question number 10, and question number 11. So they're self-explanatory. I don't think so that you will need a lot of help. If you've understood the measures of location easily, I'm sure you will get this. But still, if you don't, please let me know. Then I can arrange a session and I can explain them. Or perhaps we can have a session on Google Meet or on Zoom. If we come together, we can discuss this. So let us just go to uh, our work, and that was the measures of variability now. So the measures of variability, as we all know, they are such measurements that will actually tell us that how variable our statistical data is, and there are numerous measures for that. Indeed, there are main two types of measures of variability. The one type are um, the absolute measures of variability, whereas there are relative measures of variability as well. So bookishly, absolute measures are those that will actually tell us the variability in the units of the physical units of the data. Whereas the relative measures will tell us the same variability, but perhaps in percentages or in fractions, but they are relative. They cannot be taken uh, with physical units of the data like in absolute measures. So now let us talk about which particular measures of variability are we going to discuss. Uh, are the range, the interquartile range, the variance, the standard deviation, and the coefficient of variation. So this is a very useful measure, the standard deviation, that is used in a lot of statistical analysis because of its properties. But at the same time, we have to look at these other measures as well. So they will all do the same job. They will tell us about the variability in statistical data. So variability, simply put, is if I just draw this data set for you, and if I draw another data set for you, forgive me about this. Yes, so but you can see this is more spreaded and this is less spreaded. So this has less variability compared to this one that has more variability. So if you can draw the same in the, if I can draw through a normal curve. So let's say this curve has less variability compared to this curve. You can see that this is more spread out compared to this one. So this data will naturally has more and variability usually in statistics is measured from the center of the data. So how far apart are the observations to the left and right from this central observation? Most of the measures of variability will actually tell us that. Specifically, the variance standard deviation, they will compute variability in this respect. On the other hand, when we talk about the range is simply the distance between these extreme values. So If this is my smallest number in the data and this is my biggest number in the data, only the difference of these two is called the range. Interquartile range, on the other hand, is, I hope you remember we discussed quartiles in the previous section. So quartile number 1 was here. This is quartile 1. Quartile number 2 was here. That was in the middle. This is the second quartile. And quartile number 3, sorry, let me erase this. Oh. So quartile number 3 was somewhere here. So if we take quartile number 3 per se here, so there will be a distance between these quartiles. Okay, this is 3. So, and this was our data set. Okay, let me draw it again. Yeah. So the difference between first and third quartile, or third and first quartile, is usually called the interquartile range. So in a way, this variation will be more in a more spread out data if this is quartile number 3 and this is quartile number 1, and it will be less in a less spread out data. So the philosophy of interquartile range is that it will just tell us the difference between this third quartile and this first quartile. Okay, so let's get with it and let us see the definitions and the relative discussion for these measures of variability. So let's just move with the lecture. You can see that the coefficient of variation is there as well, but the coefficient of variation, since it is a relative measure, so naturally that is going to give us variability in a percentage form. Usually the relative measures are expressed in 100. So what is the range of data? I just told you the difference between the smallest and the largest data values. It's a very simple measure. So imagine taking the same data of 70 rental values that we took with the previous session as well, or the previous lecture as well. The difference between the smallest and the biggest. The biggest is 615, the smallest is 425, the range is 190. Interquartile range, I told you, is the difference between the third and the first quartile. Okay, so this is how we do it. I hope you remember how we found the quartiles in the previous session. So quartile number 3 was 525, quartile number 1 was 445. Just take the difference of these two, you will get the interquartile range. And this is the spread of the data. So the distance between these two numbers is the spread of the data according to the interquartile range. Now, which of these measures is good or bad? It depends actually on the situation. But by and large, I mean, if we look at the properties of the measures of dispersion or measures of variability, standard deviation is regarded as a better measure. Variance is our third take here. It's a measure of variability that actually utilizes all the data. And the concept is pretty simple. I mean, just let me give you a small little example here. If I take a few observations, very simple observations, let's say I take 10, 20, and 30. So these are my 3 observations that I have, and I want to compute the variance. Now, for the variance, I first will have to calculate the mean of the data. So what will be the mean? You know, the mean is the sum of all numbers divided by the number of observations. So if I sum up all these numbers, I get 60. And if I divide it by 3, I get 20. So 20 is the mean. Now, how will the variance compute the variability in this data? Because x bar is 20, so this x bar comes here, which is actually 20. Variance will actually compute distances of each data value from this 20. So imagine the distance between 10 and 20, 20 and 20, and 30 and 20. Okay, so what are these distances? If I subtract 10 minus 20, I get minus 10. If I take 20 minus 20, I get 0. And if I take 30 minus 20, I get plus 10. This is plus 10. Okay. And now the formula requires me, or the rule requires me to take the square of these distances. So the square of minus 10 will be 100. The square of 0 will be 0. And the square of 10 will be 100. And next, the rule demands me to take the sum of these three numbers. So I will have to take the sum of these three numbers. So the sum of these three numbers, which are actually the squares, okay, the squares of what? Of the distances of x's minus the x bar. So this was my x actually, okay, and I was taking the distance of x minus x bar. So these were my x minus x bars actually, x minus x bar. Okay, this was the bar. Let me take, yes. So this was the distance x minus x bar. This was minus 10, 0 and plus 10. And then I took the squares here. So this was xi minus x bar. And I took the whole square. So the square was 100 and 0 and 100. So the total sum of this, now I'm summing this whole thing. These are the deviations, and I took them in the squared form. So the second row was of the squares. This was the square. Okay, this is 2 actually, equals 200. Okay, variance, the definition of variance is the average of the square deviations of the observations from the mean. So that you need to take an average of now. Just divide by the number of observations. How many observations I had? 3. Just divide by 3. So I get my answer, which is actually 200 by 3. Okay, so this should be somewhere in between 60 and 70. My answer should be, but this is my answer for the variance. Okay, 200 by 3. Let us see that. I mean, let us see if we can actually compute this here. Okay. Yeah, sorry about this. So let me stop this and let me calculate this for a while. Okay, let me see if I can calculate this. 200 divided by 3 would give me 66.67. Okay, so now what will be my value? My value would be 200. That was 200 divided by 63. Okay, so the variance in my case for 10, 20, and 30 was 66.7. Now, there's a point to note here. You see, for 10, 20, and 30, the variance was, this is the variance. I'm just denoting it with sigma square. I'm assuming this is my population data. So this was 66.67. Okay. Now, what is the magic part? The magic part here is any three numbers that I would take, and if they would have these deviations of tens in between them, their answer will always be the same, no matter which values I take. Okay, for example, if I take 120, and 130, this is 20, pardon me, 130 and 140. Variance will remain the same. It will be the same variance. If I take another data value, for example, 700, this is 700, and then 710, and then 720, you will end up with the same variance. Okay, so just remember that variation is something that is going to be measured in the same way. I mean, if you take the means here, take their distances, take their squares, the deviation squares, if they're average, you will end up with the same variance and naturally the same standard deviation. So because the spread is the same, they're far apart by 10 observations, all these three data sets. So this is how the variance will be computed. Another point is, if I have a data value which is repeating itself and there is no variation, let's say I have three numbers, they're all tens, variance will be zero. There is no variance because there is no variation in the data. So variance essentially will measure if the observations are changing, if there's some amount of variability, and that is going to be measured. So give me, a minute to explain this further. If I take another data set, let's say I take a value, which is, let's say, the spread is more than that of 10 numbers. So let's say I take 100 and 200 and 300. Now the three values that I've taken so far are, they're increasing by hundreds. Okay, so this is 100, 200, and 300. What do you think? How much should be the variance? Should it be more than this or less than? Naturally, it has to be more than 66.67. You can easily use a calculator here. Um, Let me show you that how can we do that using a calculator. You have your own calculator with you. So just try this. I mean, go to the start function first. I'm already on the start function, but you have to go to setup and then go to your start function. And because you're checking the variation in the data, just press on 1 and then give the data. So if I'm computing the variance of, let's say, 10 and 20, okay, sorry, equal, and 20 and 30, okay, I just gave three data values. I just want to check the variance. So you have to press on the clear button first, go to shift, and then come back to the start button. Now what do you want? You want to check the variation in the data, press 4. Which variance you want to check? Because this is not the way, this is the standard deviation this calculator is telling me. I want to check the population variance or population standard deviation. The population sign is sigma, sample sign is small s. Just remember this. So press on 3 and press on equal. Because this was the standard deviation, I need to take the square of this in order to get my variance, because there's a small little relationship between variance and standard deviation. Variance is actually the square of standard deviation. I was coming to this, but still. So this is my answer. This is actually the variance in my data of 10, 20, and 30. So using your calculator, you can easily find these small little numbers. Okay. Now coming back to the presentation, we have computed variance, we have understood it. So one thing you must realize here, because we were squaring the observations, variance will always be in the squared units of data. The answer of variance is, let's say if I was taking my data in kilograms, Okay, if I was taking kilograms, if my data was in kilograms, variance will always result in kilograms squared. You just remember this. Okay, yes, kilogram squared. Because the rule of variance is such that it takes the observations in the squared form. Okay. So let's get to our next uh, thing in the variance. The next thing in the variance is that I just explained this formula to you. Let's come to the sample variance and the population variance. You can see the population variance is the one that I was working with. I just showed you how to compute this. Okay. You see the sample variance as well. So you see this small little difference between the population variance and the sample variance. You can see the sample variance is divided by n minus 1, whereas the population mean is divided by n. Numerator looks like the same because x bar is the sample mean and mu is the population mean. Signs are a little different. So why should we take n minus 1 from the sample? So there's a small statistical theory here that there's a concept of unbiasedness with variance. Sample variance is unbiased estimator of the population variance if we take the divisor to be n minus 1. I mean, if you take divisor to be n, it will not correctly estimate the population variance for you because sample variance is also, I mean, it's like an estimator for the population variance. It is taken like an estimator for the population variance. So it has to estimate the population variance for us. This means that this is actually um, the divisor has to be n minus 1. We cannot take the divisor to be n here. Just remember this theoretically. Okay. Now, the next thing, this I already explained to you, that standard deviation. There's a relationship between the standard deviation and the variance. Variance is the square of standard deviation. So naturally, I mean, standard deviation has to be the square root of variance. So you need to remember this, that actually, if we square the standard deviation, we get the variance. And if we take a positive square root of the variance, we will always get the standard deviation. So the next thing that we are going to discuss is the coefficient of variation. The coefficient of variation, as you were told before, that this is a relative measure of dispersion. This will tell us about the variability without taking any physical units of the data. So two things that are needed in the coefficient of variation are the standard deviation and the mean of the data. So whenever you need the coefficient of variation, make sure you have computed the mean and the standard deviation in the data, in your sample data maybe, or in your population data. So the signs are going to be different with these data sets, and just multiply it with 100. So the coefficient will always result in a percentage form. So smaller percentage reflects on smaller relative variation, and a larger percentage reflects on a bigger uh, amount of relative variation. Okay, so let's come back and let's consolidate the rules here. The formula were pretty simple. The variance denoted by S squared, this was the sample variance. You have to take the average. Now, the average is basically sum by number, but with sample variance, we know theoretically that we have to take n minus 1. And these are the deviations of the observations from the arithmetic mean of the data taken in square form and then taken in average. You can try this using your own calculators. And then the standard deviation, just take the square root of the already computed variance, you will get the standard deviation. And finally, the coefficient of variation, where we are using standard deviation and the mean of the data, and we are multiplying with 100 to get this final percentage figure, 11.15%. Now, the question may come that, okay, when should we use the standard deviation for a data set, and when should we use the coefficient of variation for a data set? Well, that is simple. I mean, if I have 2 or 3 data sets and they're in the same physical units, let's say I was comparing the weight of students in 3 different groups or classes, maybe. So naturally, the 3 groups or classes, they have, um, I mean, the weight has to be measured either in pounds or in kilograms. So kilograms for section A, kilograms for section B, and kilograms for section C can be compared. So we can use the standard deviation there. Okay? But imagine that, you know, you don't want to compare weight of all the 3 groups. Let's say there's something else that you want to compare. Let's say you want to compare the amount of variation in the marks, and perhaps the weight variation in a class, or the height variation in a third class. So because the units in the 3 groups are different now, you cannot use standard deviation. That is because it takes physical units. Variance will give us an answer in squared form of the units. The standard deviation will give us, because you're taking the square root, it will actually give you the answer in the actual units of the data. But if there are 3 groups and they're in 3 different physical units, you cannot take standard deviation. So instead, you need something relative, which is free of units, where you can compare the variation in the form of percentages perhaps for all the 3 groups. So there you use the coefficient of variation. Okay, so with this, we end up this session on the measures of variability. Um, uh, so I'll be solving a few problems from the exercises like I did before with the locational measures. That was our previous section. Read this section in the book. Try to understand the content. I'd be uploading PDF files of the solved exercises, which you can see. You can try and understand. Hopefully, they'll be understandable. But still, if you have problems, you can always come back and discuss it with me. So for now, thank you very much, and see you in the 3rd lecture, which will be about the measures of relative location and detecting outliers. Hopefully, our final one. So please read carefully the book along with it, and also try to solve a few exercises. Okay, best of luck.